Hi. So today in this video, we're gonna have a look on this new concept called lattice. Okay, and we're gonna use the supremum and infimum of a partial ordered set to define the join and meet of those elements in the partial ordered set, and then we're gonna use those notations to define this lattice. Okay, so good. So let's begin. Okay, so let's suppose, okay, the set X and a partial order, a binary relation R. Okay, so this is a partial order set. Okay, sometimes we call this as PO set, right? So just in short. Okay, so I'm gonna have for elements X, Y in this X. Okay, then we can denote some notations. Okay, when we are saying we're gonna have this join, so we mean that, so we write this join as X, this notation. Okay, so this is sort of like the union, but we have this angle, right? So this is more like a V. So join in X, so this is the set X, okay, with Y. So this is gonna be defined as the supremum over X for those two elements, okay? And we say that a meet of those two elements, so we're gonna use this, right? Okay, and this is gonna be the infimum of X and Y. Okay, so now we're gonna use the join and meet to define the lattice. Okay, so we call it a partial order set X and R. It is a lattice. Okay, if for all X and Y, so the X and Y's join and meet both exist. Okay. Okay, so this is a pretty straightforward definition, and then we're gonna have a quick look on some examples. Okay, so and it's very natural. We're gonna know that the Rn with the greater than or equal sign that we defined previously, that would be a lattice, right? So say Rn, or like maybe we just use another simple example, right? Let's say, for instance, R2, okay, is a lattice, okay. So we're gonna have a look on this R2 and with greater than or equal sign. So let's say for all X, Y in R2, okay, so we're gonna have the join to be the sup of X and Y. Okay, so that's gonna be the max of X and Y in the first dimension and the X and Y in the second dimension, right? Okay, so that's gonna be our join, right? And the meet would be the minimum, right? Or the infimum, and that would be the minimum. Okay. And it's the same for Rn, okay? So the same thing. All right, so geometrically, okay, let's say this is point x. Okay, this is point y. So this is the first dimension, and this is the second dimension. Okay. Okay, so then we can immediately observe that. So when we connect those two dots, then this point, that'll be the maximum. That'll be the that's gonna be the join, right? So x join y, and this is gonna be the x meet y. Okay, under R2. Good. So that'll be a good example. Okay, and remember that we also had a partial order set, right? A very nice example where we have the power set and the contain. So this is also true. That is a lattice, okay? And we can even map those join and meet to the union and intersection, right? Exactly, and they also look pretty similar, right? Okay. Let's say for two set A and B, which is an element of this power set. So remember that the power set, that'll be just the set of all subsets, okay, about this X. Okay, so let's say A join B over this 2 to the X to the power set, and that's gonna be the A union B, right? And when they meet B, and that's gonna be A intersects B. Okay, good, and this is a very natural example. Okay, so then we're gonna have a look on some example that is not a lattice. Okay, so a way to construct a counterexample, so we can just remove the sup or the inf from the set, right? So we can just make it disappear, and then then that would be not a lattice, right? So let's say some x is such that we're gonna have 0, 1 and 1, 0, okay? And this is in R2. And then there's x and greater than or equal sign. So this is not lattice. Okay. And this is because both of the either the sup and the inf is not inside of this X, right? It's not contained in X. Okay. Or it's going to be inf, right? Does not exist. Okay, good. All right, but if we add something, if we add some elements inside of X, let's say we put maybe 2, 2 or 3, 3, and let's put a 0, 0 to the X, then this is gonna be a lattice, right? So now the both of the sup and inf, they exist, right? Okay, good. So this is a counterexample, and then we're gonna have another counterexample, okay? And this it's also using the same logic, okay, to try to construct some kind of example where we just remove the sup or inf, okay. So that the previous one in example 3, this is one way of doing that, right? So another way of doing this counterexample is that remember that this sup and inf, they're gonna be some limit, right? So if we just have some empty circle, okay, and remove some limit, then also that limit doesn't exist, and then the sup and if doesn't exist, right? So that's another way of constructing this kind of example. So let's say we have this x to be 0, 0, okay, and 2, 0, and 0, 2, and then, so this is one part, okay, and then I'm gonna union this with some ray. Let's say for x1, x2, the set is gonna be x1 equals x2, okay, for x1 is greater than 2. Okay, so it doesn't include this point of 2, 2. Okay, so that's the point. Okay, so let's have a look on this figure. Okay, so what we mean here is that we have this point 0, 0, and 0, 2, and 2, 0. Okay, we're gonna also have something here, okay, that's array starting from this point, but we do not have this point, so this is empty circle. Okay, so this doesn't include the boundary, and then there's also the supremum is also not existing, right? So this is not a lattice for another quick example. Okay, good. So and finally we're gonna introduce another definition on the sublattice. Okay, so let's define the sublattice. Okay, so we say that for a lattice x and r, okay, we're gonna say this set S as a subset of X is a sublattice of this XR if we're gonna have for all elements XY in S, we're gonna have the sup, okay, or the join is inside of S, and we also have the meet is also inside of S. Okay, and but be careful that we're having this operation, those two operations under X. Okay, so this is very important. Okay, so now let's have example, a good example of a sublattice. Okay, let's say this S is gonna be 0, 0. This is another example in R2, 1, 0, 0, 1, and 1, 1. Okay, so this is R2. So that is a sublattice of the R2 greater than or equals. Okay, because the either of the sup or inf of any of those two elements is included here. Okay, but more importantly, we're gonna do those operations of the join and meets under this X. Okay, so this is more important. Okay, and for another example, a counterexample that is not a sublattice, let's say this S is changing to 0, 0, 1, 0, 0, 1, but 2, 2, okay. Again in R2, this is gonna not be a sublattice of R2 greater than or equals, okay. This is simply because, for example, the join, okay, the join of 1, 0 and 0, 1, okay, so this is gonna be the join over R2, right? So this is very important. So that's gonna be the sup of those two. So we're gonna take the maximum, right? So that has to be 1, 1. But 1, 1 is not included in this S, right? So this is not the sublattice. Okay, good. So in this episode, we discussed, we defined the lattice and sublattice, and based on the previous definitions for the partial ordered set with the some important operations such as the sup and inf, the join and meet, which are further defined on the sup and inf, right? So, and this lattice structure is pretty important for us to define some things later. Okay, so that'll be everything for this episode. Good.